So in the second part of 4.4, we're looking at a way, hopefully, to identify local extrema even more easily, more quickly, more efficiently. This is where the second derivative test comes in, which, appropriately named, right, involves the second derivative of x, right? Um, Unlike the last problem, I'm actually going to jump right into the rules and the results. Um, so kind of how this works. First and foremost, my first thing to do is, well, to get to the second derivative, I have to start by finding the first derivative, and it will be helpful later if while I'm here I also identify the critical points or the turning points or the stationary points, critical, whatever you want to call them. Remember, that's where the function, the derivative of the function is equal to 0. Well, the next thing I want to do with the second derivative test, well, part of what I want to do, I suppose, is to find the second derivative. And I want to evaluate the second derivative at all critical points. So at this part, for this, if we let some number c be a critical point, then we have a couple outcomes. One, so obviously it's a critical point, so the first derivative is 0. So if the derivative at c is 0, and the second derivative, the second derivative is negative, then f has a local max at c. Right, if the second derivative is negative, then we have a negative slope. Our first derivative is decreasing, so we're moving from positive to negative. Excuse me. So we have a maximum. Makes sense? And if the second derivative is positive, well, then the opposite is true. Has a local min at x equal to c. All right, well, I've talked about less than and greater than. What about equal to? If for some reason both are 0, the test is inconclusive. I can't really use it. I should just stick with my first derivative test instead. Now, the other thing, though, that the second derivative test is useful for, and part of the reason why this right here isn't entirely useless, is for something called concavity. Right, whether or not my graph is some sort of concave up, right, it's kind of opening up, or maybe it's opening down. That's kind of what we're talking about with concavity. Well, what I'm going to do is I need to find, for this, it's going to follow very much what we did with the first derivative test, where I'm going to find the second derivative and all of the x's where the second derivative is 0. And just like before, we're going to make a sign chart and test intervals, and here are my results. If the second derivative is positive, then the graph is concave up on that interval. If the second derivative is negative, the graph is concave down. And if the second derivative is equal to 0, these points that I asked you to find in the first place, we call these possible inflection points, points of inflection. What is an inflection point? An inflection point just means I have some sort of change in concavity. All right, so I'm either moving from concave up to concave down. Maybe that would look something like this. Right? If I kind of were to draw a line between the two, you can see a point where I'm concave up and a point where I'm concave down. Obviously, the opposite could be true. point where I'm concave down, concave up, I might have a change in concavity. I should check and see if I do. So if we start to work with this now, if we were to kind of go off of that, we're going to consider this function, which is actually the function that we worked on in part 1. I want to know the intervals in which f is concave up or concave down, and I also want to know the nature of any turning points. So here's my graph of f. Noticed I've already marked in the x value of any maxes and mins, any turning points, my horizontal tangents. So that's kind of saved yourself some time, right? If you remember, I'll stick with a different color here. If you remember, I had taken my derivative, I had determined that my turning points, or my critical points, were when x was negative 2.12 and 0.786. Okay, great. So let's determine the nature of those turning points. Well, to do that, I need to know the second derivative. So I'm just going to take my first derivative and derive it again. So I get 6x plus 4, which we'll come back to this when we do concavity later. But for now, we'll apply my second derivative test, and I'll stick with like a similar color just to group things together. So using my second derivative test, we're going to take f double prime of negative 2.12. And I've done this already to save ourselves some time. We get negative 8.72. And I'm going to do this again with 0.786. And oddly enough, I get positive 8.72. No confusion here. Let's just get rid of that little dot. So what does this tell us? Well, at negative 2.12, my second derivative is negative, which of course tells me that I have a maximum. And then at 0.786, my second derivative is positive, so I have a minimum. So that's all I'm saying with using the second derivative test to determine the nature of my turning points. And you can see that right on the graph. Here's my max, here's my min. Okay, great. So the next thing I want to do is determine the intervals that f is concave up or concave down. So to do that, this process is going to very much resemble the first derivative test. So I need my second derivative equal to 0. Well, fortunately, I've already done that. Of course, I'm going to get negative 4 over 6, which is negative 2 over 3. This is going to be a possible inflection point. At this point, I may change concavity. We'll see if that's true. But for now, we're just going to kind of mark that. So negative 2/3 is maybe about, I don't know, here-ish. So just so we have it in there, just to kind of see where things are going, maybe I'll pick a better color. So just to see kind of a visual, maybe it's about here. I'll highlight it in green just so it sticks out. We have a reference here. Potential inflection point. We'll see what happens. We're going to create our sign chart around that value that I get. And we're going to test points. So something bigger than negative 2/3, 0 would be particularly useful here. Right, the easier numbers I can pick, the better. So negative 1 would be helpful as well. I want to evaluate the sign of f double prime. If I plug in negative 1, negative 6 plus 4 is negative 2, so I get a negative value for f double prime. If I plug something in 0, I get a positive number. Of course, I actually already kind of have that. I realize now we have negative 2.2 and 0.786 here that I could have used as test values, but it's okay. The extra work never hurt anybody. So I have a negative value here. What does that tell me? Well, from my concavity test, we were concave down here. And I have a positive value over here for 0, so that tells me we're concave up here. So I'm going to state my final results as saying that f is concave up on the interval -2/3 to infinity, and f is concave down on the interval -infinity to -2/3. Again, these are open intervals again because at 2/3 specifically, this is neither concave up nor concave down. The concavity is changing, as we can see. So this is absolutely 100% a point of inflection. So that's kind of our second derivative test in a nutshell. How do we start to use this? Well, before we do that, the most important thing that I want to remind you guys, my pro tip here, is that it is really important before, but now, especially moving forward with this application, I'm going to show you, you need to be organized. You want to be meticulous with your setup. This isn't just for yourself. Sorry, this isn't just for like the IB graders. This isn't just for me trying to grade your test. This is for you too. You really want to be organized here. You really want to show and identify where things are being done, so that way you can go back and use it too and find it really quickly. So one thing we're going to use all of these tests for is for what we call curve sketching. So if I were to give you a whole bunch of features of a graph, or just give you a graph and ask you to sketch either the function or the derivative of a function, how do you do it? Can you do it? Well, the answer, of course, is yes, you can. But first, some things that might be a little bit helpful first. So the critical numbers of f, as we said before, are the zeros of f prime, right? How did we find the critical numbers? We derived the function and then set it equal to 0. Likewise, the criticals of f prime are the zeros of f double prime. Let's take it one step farther. Remember from our first derivative test that f is increasing if f prime is greater than 0, it's positive. F is decreasing if f prime is negative. From what we just learned, f is concave up if the second derivative is positive, and concave down if the second derivative is negative. And of course, our inflection points of f are where the second derivative is equal to 0. Criticals, or extrema, by the way, or turning points, or whatever. The other thing that might be helpful is to start putting together increasing and decreasing and concavity. So a function I have can either be increasing or decreasing. A function I have at any point could be concave up. I'm just going to write CU and CD. Up and concave down. These shapes are going to help us start sketching our graph, right? The more I can identify shapes, the more easily we can kind of eyeball this graph, right? So if I'm increasing, I have some kind of a positive slope, but I'm concave up, so I also want to point upward. So increasing concave up is going to kind of swoop up like this. It would make sense then that decreasing concave up is just going to be the other half of that swoop. Increasing concave down, I need a upward moving line, but it needs to open down. So kind of this. And my decreasing concave down will kind of finish off that little upside down bowl shape. So these are the 4 shapes that are going to be super helpful to us in curve sketching. I think this pro tip again was supposed to be just to stay organized. It's really important again to stay organized. Making a chart seems to help me out when I do these problems. Hopefully it'll help you out too. It's just a sketch. It does not need to be perfect. All right, so here's my first curve. If I have f below, as I have here, sketch f prime and f double prime. We're going to take this one piece at a time. What do we know already? Well, we know some things that would be helpful to know about f prime would be the zeros. Would be where it's maybe positive or negative. Concavity is not something we're really going to get with f prime, right? Because you need to be two derivatives out, so we're not going to worry about that. Possibly turning points could be helpful. Maybe. Let's see what happens. Well, zeros would definitely be helpful. We said before, zeros occur when the derivative, at turning points of f. So where are my local max and min? They are right here, they're right here, they're right here. For a graph like this, it's relatively easy just to map everything right on. So if I have a zero at these, a max or min at these blue dots, the zeros will be at the same x-coordinate, just now on the x-axis. So here are my zeros. The next thing that might be helpful is where is the function positive or negative? Well, the first derivative is positive if we kind of think about our first derivative test in reverse, wherever the function is increasing. And of course, negative wherever the function is decreasing. Well, where is it increasing and decreasing? It's increasing and decreasing between all of these turning points. Right, so obviously here we're kind of decreasing here, a lot of increasing going on over here, some decreasing and some increasing. Nothing about this has to be perfect. If I just call these points, I don't know, let me get rid of all the D's and I's, just like A, B, and C, just to kind of have an idea of what's going on, and I start to think about this on a sort of chart. We said that the function is decreasing until A, and then increasing, and decreasing, and then increasing, right? Which means that the derivative is negative where it's decreasing, positive where it's increasing, negative, positive. So here's how we're going to attack this. We're just going to eyeball it. Nothing about this has to be perfect. It's just a sketch. I know that around A, I'm moving from negative values to positive values. So I just know somewhere around here, I'm going from negative to positive. And I'm just going to draw that little tick mark in just as a guide right now. I know that around B, I'm going from positive to negative. So I got to look kind of like this. And then around C, I'm going from negative to positive. So now I've got my little tick marks to help me. And you can maybe start to see the curves of this graph start to take shape. If we were to consider the turning points, this would kind of be backed up too. This is where the second derivative is 0, right? The derivative of the derivative, which is, loosely here, loosely here. As long as I'm hitting my maxes or mins somewhere around there, I'm okay. But for this graph, I don't find it super helpful to look at it that way because I'm not actually trying to hit those function values. It's just the x value where I need to peak, but it's going to happen with a guide like this. So I know I'm coming from negative. No information tells me beforehand that I'm going any higher or lower. I'm crossing the x-axis because I need to. I'm peaking and returning to the x-axis to cross it at B because I need to go from positive to negative. I'm going to curve around again so I can get to C and go from negative to positive like I need to. And nothing tells me that I'm changing direction anywhere else, so I'm just going to continue to increase. And there is my first derivative. I'm going to follow the same process for the second derivative, and for the sake of my eyes, I'm just going to copy this whole table over and erase the first function. So that way I can focus on what's important. I can focus on the second derivative, the first derivative, which I need to now derive again. we're going to follow the same process. It would help maybe if I knew zeros of f double prime. It would help if I knew where it was positive or negative. The turning points didn't really seem all that helpful, so we're not going to worry about it this time. Well, the zeros of f double prime are at the turning points of f prime. So that would be here-ish and here-ish. So I'm just going to mark those. Let me get rid of my letters too so I can write some new letters in. So again, if we want to maybe make a chart to help us out here, we'll call these points A and B. Because right now we don't really care what they actually are. Then at A and B, let's see kind of what's happening around it, right? If I pick anything less than A for an x value, my function is decreasing, which means the second derivative is negative. Oh, that's backwards. Sorry. We're increasing, so we're positive. Whoops. And then between A and B, we're decreasing, so negative, and then increasing again, so we're positive. So we can kind of sketch it out the way we did before, right? I need to increase, and I need to decrease, and then go from negative to positive, right? So I'm going positive, negative, negative to positive. Again, you can kind of start to see the curve of this graph take shape. So if I were to sketch it in, something like this maybe would be my second derivative of f.